1, 0.
Uno, dos, tres, cuatro.
Hi everyone, today we're going to look at solving and proving trig identities. So it's an extension from 7.1 in which we look to simplify identities. Today we're going to have a little more structure in terms of having something that we need to balance a left side and a right side. So today's lesson has a bunch of rules that we want to take a look at, and maybe not so much rules as in terms of guidelines of if you follow these steps, and if you follow these steps in order, at some point you'll be able to solve the questions that you're going to have for today. So it's not the be-all end-all, but I know that when I look to solve and prove identities, this is something in which I follow. So I'll talk about the steps quickly, and then I'll try to refresh them as we go along in each of the examples we have for today. So similar to many things that we do, we want to factor if possible. So take a look and see if there's anything that you can pull out, or if there's anything that could look cleaner by being able to factor something, and potentially that might help you simplify in any of your expressions that you have there. So after you factor, we want to write things in some sort of common trig language. So for me, I think the best way is to try and change everything to sine and cosine. If you think about it, we have sines, cosines, tans. We now have cosecants, secants, and cotangents. If we can reduce the number of trig terms that we use, and we could just refer to something in terms of sines and cosines, for the majority of questions, that's really going to help us. And I mean, there could be the odd exception in which it doesn't, but I would say definitely that's something we should take a look at. The next is trying to write everything as a single fraction. And finally, it would be, if you can't do anything else, we're going to apply something called the conjugate, which you may remember from Math 10 and Pre-Calc 11. So let's take a look at what it means to be able to prove an identity. Here's a couple examples. And if you look at this first example right now, what it's saying is, it's saying prove that this statement is true. It's saying cosecant squared x minus 1 over cosecant squared x, prove that that is equal to cosine squared x. And if we want to prove something, we need to draw a line down here. And what we're going to do is we're not going to write equal signs until the very end, because if you can write an equal sign along the way, then you're prematurely saying that they're already equal to each other. And we haven't done that. That's our goal, is to be able to say that, yes, they are exactly the same. So this first example, what we want to do is we want to see what we could potentially simplify. And so there's a couple things that we should set up here. So whenever you have an identity and you're trying to solve one of these or prove them, you want to draw a line down the middle, and what happens on the left side stays on the left side, and what happens on the right side stays on the right side. So you can't cross or bring anything over, because that would imply an equal sign. The second thing is you're allowed to work with both the left side separately and then the right side separately. It's not that you're stuck with having to only work with one side. And if we look at what we have right here, we do have cosine squared x, in which there's not too much that we're going to be able to do with that. But the left side, probably we're going to be able to try to simplify and adjust some things to make it look a little bit better than what it does right now. So there's multiple ways that we can approach this. And one of the challenges of identities is to see what's the best step. And sometimes the best step isn't always obvious. And in this case, if you see cosecant squared x minus 1, we actually have a couple choices. We could change cosecant squared x to say 1 over sine squared x, and that would probably be a pretty good decision. Or you could also refer back to your identity sheet and see what we have with something on there. So for instance, if you look at the Pythagorean identities, I'm just going to write this on the side here. One of your Pythagorean identities was to say 1 plus cotangent squared theta was equal to cosecant squared theta. Or another way of being able to simplify that could be subtracting 1 to both sides and saying that we also wrote at some point that cotan squared theta was equal to cosecant squared theta minus 1. This is something that we had shown on our identity sheet. So what you could do is you could look at the top right here where it says cosecant squared x minus 1. you could replace that with cotangent squared x. So let's do that and see if that's going to help us out. And then we'll just leave cosecant squared x as it is. Okay, so think about the steps of what we said. So step number 1 was factor if you can, or potentially look at some of the Pythagorean identities, which we did. And step number 2 is to get a common language and change everything into sines and cosines. So where it says cotangent squared x, let's remember that cotangent is the same as saying cosine over sine. So you could replace that and say we have cosine squared x over sine squared x. And it's all being divided by, instead of saying cosecant squared x, you could write that as 1 minus sine squared x. Now we have a fraction divided by a fraction, and our third step says whenever you can, you want to turn things into single fractions. And so if we have a fraction over a fraction, we know that we would multiply by the reciprocal. In other words, this 1 minus sine squared x, we're going to say that we're going to times the numerator by the reciprocal, which is sine squared x over 1. That reduces this guy here. And if you take a look at that and you have sine squared x and sine squared x, they simplify with each other. The variables reduce and you're left with just cosine squared x, which would be equal to the cosine squared x on the right side. So you could say something like the left side is equal to the right side, or you could put a big check mark, and then you're basically saying that we're balanced. The left side is equivalent to the right side. Last year we had Karash, and he loved to sign his name, and his autograph was his way of saying that I've balanced the left side with the right side. So whatever you need to do, just do something to be able to show that they're equivalent to each other. Notice that the process is everything here. The way that you show your work, the clarity around it is what gets you all of the part marks to be able to show that you can fully understand something like this. So you want to make sure that that's very, very clear as you go along the way. We can't just jump to the final step and show that the left side's equivalent to the right side. So it's actually very easy to gain some part marks along the way. Finally, you can look this up. There's a Latin phrase. I wouldn't want to try and pronounce it right now, but if you look it up, QED is a way for saying that we are balanced in Latin, and it's a way for being able to, sometimes it's written when you do a proof. Okay, so that's our first official proof. Let's take a look at the second one, and let's see what we could do with this right here. Okay, so we draw our line down the middle. We have our left side and we have our right side. And if I look at the left side, I would say that right now is not a single fraction. If I go in order, I should first say there's nothing we could factor out. And then I would say everything is in terms of sines and cosines. So step number 3 would say, let's turn that into a single fraction. And my lowest common denominator is 1 minus cos x times 1 plus cos x. So I could times this bottom left by 1 plus cos x, and then I times this by 1 plus cos x. And then over here I'd say 1 minus cos x, and here I'd do 1 minus cos x. And if we did that, I could write that all under single fraction. And here we would say we have 1 plus cos x times by 1 minus cos x. And on the top, I would have 1 plus cos x plus 1 minus cos x. If I want to simplify some things here, I could look at the top and I could say, do I have any like terms? And I do. The 1 plus 1 could add together and we could create 2. And then the cos x minus the cos x would reduce with each other and cancel out completely. So we just have 2 on the numerator. And then on the denominator here, you have 1 plus cos x over 1 minus cos x. So this is where it gets a little bit gray. If you're not sure and you haven't balanced out the left side and the right side, imagine what would happen if you foiled this out to see if you could potentially rewrite it in a different way. And so if you do foil that out, you would recognize that you had a difference of squares. So you would say 1 minus cos x plus cos x. The 2 middle terms are going to cancel each other out, so I won't even bother writing them. And then minus cos squared x. And that's important because once we create something there that says 1 minus cos squared x, I would look back to my identity sheet and I would think about some of those Pythagorean identities. Specifically, there's the Pythagorean identity that says, let's just write this up over here, that says sine squared x plus cos squared x equals 1. And if I manipulate that, which we're allowed to do, then I know that sine squared x is equal to 1 minus cos squared x, which means that I could replace this denominator with a sine squared x. And if I do that, I know that I'm almost done, because 2 times cosecant squared x is going to be equivalent to 2 times 1 over sine squared x, which is just like saying 2 over sine squared x, and they are balanced. QED. So we know that the left side's equal to the right side there, and it's one of those things where when you walk out of your quiz or your test, you can feel very confident that you've nailed it, because you know that the left side equal the right side from all the work that you showed from there. You can feel pretty good about these questions. Okay, let's keep going and let's look at a couple more examples. Okay, example 3. So I think the best thing to do is just to continue to say over and over the steps in the process for that. So step number 1 is to see if there's anything we could factor out. There's nothing that we could factor out in the left side or on the right side. There's no Pythagorean identity that would exist there either. Step number 2 would be to change everything to sines and cosines. And so we actually have quite a bit that we can do with this one. And we want to work with both the left side and the right side. So instead of saying tan, I would change that into saying sine over cosine. And then instead of saying cotan, we can say that's cosine over sine. And if you want right away, you could move on to the right side. You could start working with that. Instead of saying secant, I could say that's 1 over cosine, and it's being times by 1 over sine. And on the right side, I could actually then say, well, I can just say that's like saying 1 over cos x sine x, and we're done with that. There's nothing more that we could do on the right side, but on the left side, if you think about what step 3 is, it's to change everything into a single fraction. So if we want to change everything into a single fraction, we have a lowest common denominator of sine x and cos x. So the bottom left needs a sine x, so then the top left gets a sine x. And then the bottom right needs a cos x, so then the top right needs a cos x. And if we do that, we now have a common denominator of cos x sine x. The order that we write that in doesn't make a difference. If I say the variables AB, I know it's the same as saying BA. So for this, we can say sine x cos x, or you could say cos x sine x. On the top, we have sine x times sine x. And so think about what would happen if you had the variable a and you times it by a. A times a would equal a squared. So that means that if you have something like sine x times sine x is going to equal sine squared x. And cos x times cos x is going to equal cos squared x. So we've gone through our first 3 steps, and there's nothing really more that we can do except we want to keep revisiting. If I've gone through step 1, step 2, step 3, if I go back, is there something that I could now do that I couldn't have done before? And there is. We have a Pythagorean identity on our top left here where it says sine squared x plus cos squared x, because we know that sine squared x plus cos squared x is equal to 1. And so if you replace this numerator right here with a 1, we now have them balanced, and we can say that we've proven that identity. Okay, so now that you've done a few of these, I would ask you to work on example 4, but I would say that I think that we're going to learn something new here. So let's continue to do this one together, unless you're feeling really confident about applying that final 4th step. Take a look here, and let's see what we can do. Step 1. Let's see if we could factor anything out, and I don't think that there is. There's definitely not a Pythagorean identity there either. So step 2 would be change everything into sines and cosines. So if we take a look at cosecant, we could change that to 1 over sine x, and we could change cotangent into cos x over sine x. And because they already have a common denominator, let's join that right away. So they share a common denominator of sine x. So our numerator would be 1 plus cos x over the sine x right there. If I look at the right side and I look at the left side, they aren't the same. They look like they have similar characteristics, but they're not the same. And so if I'm just going to rewrite this right side, sine x over 1 minus cos x. And so if you go through the steps and we've have everything where they're in terms of sines and cosines, and step 3 they are single fractions, there's really nothing more we can do except to say, hey, potentially I could look at step number 4. And so step number 4 would be to apply the conjugate. And you could apply the conjugate to the left side or the right side, and you could apply it to a numerator as well as to a denominator. So I'm going to work with the right side, but we could have just as easily worked with the left side too. And here's how a conjugate works. If you have 1 minus cos x on the bottom right here, I could times it by 1 plus cos x. That's its conjugate. It's the same terms, but the subtraction sign now becomes an addition sign. It's the opposite sign. Whatever you times to the bottom, you know you times to the top. So I'm going to times this top by 1 plus cos x. And let's see what happens here. So on the denominator, I have 1 minus cos x times 1 plus cos x. I could FOIL that out, and if I do, I would get, well, 1 times 1 gives me 1. But because I have plus cos x minus cos x for my two middle terms, they're going to cancel each other out, so I don't need to write that. And I would get 1 minus cos squared x. And if I look at the top, I'm just going to copy out what I have. I'm not going to expand that. And I have 1 sine x times 1 plus cos x. Okay, so given something like that, we could say, well, there is a little bit more that we can do. The 1 minus cos squared x on the bottom, if I look back and I look at my Pythagorean identities and I say, well, I know that sine squared x plus cos squared x equals 1. Let's just write that again. Sine squared x plus cos squared x equals 1. We had manipulated that to say that, sine squared x is equal to 1 minus cos squared x, which means that I can replace this denominator, the 1 minus cos squared x, with sine squared x. So if I have a sine x that's been factored out on the numerator and I have a sine squared x on the bottom, they can reduce with each other. The sine x on top will reduce with one of the sine x's on the bottom, and I would get 1 plus cos x over sine x, and these two would be exactly the same. So we've balanced them right there. Okay, so that's applying the conjugate, which is something that was a little bit new. We'll try one final example. Now that there's no more new rules, I would say, why don't we pause the video there, and you should give example 5 a try to see if you're able to balance this out, and then come back and we can see if we did it the same way or if we did it a different way. Okay, taking a look at what we have right here, I would say if I was to look at the right side, there's not a whole lot that we can do here. We have 1 minus cos x over cos x. There's really not too much we could do. There's a lot of wrong things that we could consider. I know someone might say, well, can you cancel out the cos x's? And we definitely can't do that. That would be some severe cancelitis right there. What we could do is on the left side, we could consider trying to change something into a different form. And we do have several options of different things we could take a look at. So I'm going to show you the most efficient way, though it might not be the most obvious way. And if you want, ask me in class for another way to be able to look at this. So because we're new to this, I would say it probably would be common to try to change tan squared x into sine squared x over cos squared x, and then change the denominator to say 1 plus 1 over cosine x and somehow create single fractions, and eventually that would balance out with the right side. And that's definitely a good approach of how to do something. Taking a look at this though, when you see that tan squared x, you probably want to refer back to your Pythagorean identities. And if you have 1 plus tan squared x equals secant squared x, we know that tan squared x is equal to secant squared x minus 1. And because the denominator is in terms of secants, we might want to do something with that because that might help us get there a little bit faster. So I'm going to change the tan squared x to say secant squared x minus 1. And then the denominator here is 1 plus secant x. So what we are allowed to do is that top is a difference of squares. And if it's a difference of squares, you could factor it. And if we factored that, you would get something that would say secant x plus 1, secant x minus 1. And if you take a look at that, you could say, well, my top left term, secant x plus 1, is equivalent to 1 plus secant x. Those are the exact same. They're equivalent to each other, so we could reduce them, and you'd be left with secant x minus 1. So you could rewrite that, and I'm actually going to do that over here, and I'm going to rewrite that and say that that's 1 over cos x minus 1. And then let's turn that into a single fraction. So we could write this over 1, and we could say let's times this by cosine, and let's times this by cosine. And then we would have a common denominator of cos x, and our numerator would say 1 subtract cos x, and that would be equivalent to the right side. So we've successfully done that. That's definitely a pretty tricky example. So this lesson can be fairly complicated. I would say it's the type of thing where once you get it, you really, really get it. And so when we assign these questions here, 1 to 21 odds, what I would recommend is start working on them. Ask all of the questions that you can't get to some of your classmates, to myself. But what you want to be able to do is you want to say, you'll know when you can get it, where you could face any one of the questions, 1 to 21, and you'd be able to answer them. And that's how many you should do. So if it means that you have to work on some of the even numbers too, then you could do that. If it means that you get it right away, then that's pretty good. But it's definitely something that's an important part of math, being able to prove something. And I think you'll find the homework that there's some pretty challenging questions, and you'll probably be a little frustrated that there's not enough room to be able to write your proofs. So that's all for today, and we'll definitely go over a couple more of these in class as well. Thanks.